Hello everyone, in this work we are going to apply the TTS methods for music to audio synthesis. This is a joint work with Dr. Cooper and Professor Yamagishi. I'm the second author. Music generation is a new topic for us. When we read the papers, we notice there are similarities between these two domains. For example, the speech recognition, music transcription, also the language modeling, and the voice conversion and timbre conversion. Of course, for this work, we're focusing on converting the symbolic input to the waveform. So in this case, TTS and the MIDI to audio synthesis. For MIDI to audio synthesis, we borrow the TTS framework. As you can see, we use the acoustic model and waveform model to convert the input into the output. Of course, there are a few differences. The first one is for MIDI to audio synthesis, the pitch of generated audio is quite important. It determines on the perception of the note. Another difference is, of course, on the input side. The input for the MIDI to audio synthesis is a music score or other kinds of representation that is compatible with MIDI specification. So we use MIDI API to convert the music score into the MIDI piano roll. The piano roll is the kind of representation that specify which key we should play and which time and how strong we should play the key. So this is the input features. Although it's called piano roll, but actually it can be used for many instruments. So let's look at one example. Let's just look at one frame of the input features. In the TTS case, we may have the phone ID or syllable ID, other linguistic information, although not all of them are necessary for the advanced models. For the music case, the vector of one frame specifies what kind of key we hit, and also the velocity, basically how strong we play the key at that frame. So these are the input informations that we need for the acoustic feature, for the acoustic models. Another difference in terms of the input features, as you may see here, is the length of the input features. There are two cases. This corresponds to two applications of MIDI to audio synthesis. The first application is the silent instrument. In this case, the user just wants the model to play the input MIDI as exactly follow the input MIDI. So the input MIDI piano roll has the same length as the acoustic features. They are well aligned. While for the second case, which we call AI performer, here the model might add additional professional expression to the input MIDI configuration specification. We may need to change the duration of one specific note to make it sound more like a professional performer. So these are the two applications. While for this task, since this is a preliminary work, so we focus on the simple task, where the input of the acoustic model is aligned with the output. So giving all this kind of information, you can imagine there are many TTS acoustic models and waveform models we can adopt for the MIDI to audio synthesis task. So this is the basic motivation for this work. So let's see how we organize the experiments and what kind of model we include. For the acoustic model, the first model we use is the Talktron. Although this is not necessary because the task is simple, the input and output is well aligned, but we still want to know whether the Talktron can work in this case. We build a few variants of the Talktron models. The first one is Talktron 2. So it's basically same as original Talktron. The Talktron we proposed in previous year. So in this case, we just downsampling the input by changing the reduction factor. The second case is slightly different. So in this case, we fit in the piano roll into the prenet. By doing so, we hope the piano roll can put a strong prior constraint on what kind of attention we can learn by the attention mechanism in the decoder. The last one is meaningful ablation test, where we remove this additional link to the prenet. In addition to the Toctron model, the sequence-to-sequence model, we also include one model from the music field. So it's called performance net. This is specifically designed for this application. So the input and output have the same length. So it's a feed-forward network with convolution layers. So this is a reference model we will include in the experiment. In terms of acoustic features, we have two choices. The first one is the mere spectrogram. The second one is MIDI filter bank spectrogram. These two types of features are quite similar, except that for the MIDI filter bank, we use a filter bank designed based on the MIDI frequency. For example, if we want to put a filter for this note E8, we put this filter around the frequency corresponding to this note. So the difference is basically the wrapping of the frequency scale. If we look at the compare this two types of spectrogram, we can notice the MIDI filter bank spectrogram emphasize more on the low frequency band. The reason to use this MIDI filter bank spectrogram is that it has the closer relationship with the piano roll. So as you can see from this picture, the mapping from the piano roll to the MIDI filter bank spectrogram is considered to be easier than that from the piano roll to the mirror spectrogram. For the waveform model, we borrowed the neural source filter model proposed for music, but in this case, we removed the harmonic plus noise structure. There is one thing called excitation signal. It's either the noise or the sine waveform. I will explain this configuration later in the experiment part. Okay, these are all the components we would like to compare in the experiments. For the experiments, we use the Maestro version 2 database. This database is a piano database. It's well designed for this task because the MIDI was recorded when the pianist played the piano, so the alignment between the audio and piano roll is quite good. So we just use this database for this task. For the experiments, we follow the official split of the training, validation, and test set. And we downsample waveforms to 24 kHz for the experiments. This table lists all the experiment models. The first two are softwares that converts the MIDI into the audio waveform. One is based on the sample-based approach. Another one is physical model-based approach. Here, one model shown here is the original performance net. So this model directly generates a spectrogram and uses the Griffin limb to generate the audio waveform. For the main experiment part, we include two groups of systems. The first one is for copy synthesis. So in this case, the acoustic features are natural acoustic features, either the MIDI filter bank feature or mirror spectrogram. And the excitation is slightly different. One is a completely random noise. So in this case, the model must learn the pitch from the input acoustic features. The first one is a sine excitation-based model. So it extracts the sine excitation from the MIDI API. So I can explain the details in the appendix. For the second group of models, it's a MIDI-to-Audio Synthesis. So as you can see here, the acoustic model can be Toctron, its variants, or the performance net. The acoustic features can be mirror spectrogram or MIDI filter bank. And yes, the waveform can also receive the excitation from sine or noise. So here's the listen test result where we conduct a large-scale crowdsourcing listen test. More than 200 non-professional participants rated the audios. There are many results we can read from this chart, but let me explain it one by one. First, let's compare the natural waveform with the two softwares. So as you can notice, the two softwares can synthesize high-quality audios. especially the piano take slightly higher natural sound, although the difference is not statistically significant. In terms of the neural waveform models, as we can see here, them are quite close to the natural speech, and the difference is not statistically significant. Let's play some audios. First one, the natural one, the two software wells, and the first one of these copy synthesis systems. So probably you may hear the difference between these four groups, especially the two software wells don't really sound like the natural audio because they are not trainable models. They are based on the sample or a fixed phasing model. While for the neural waveform model, it works quite well in this copy synthesis condition and can capture this reverberation effect in the natural sound. However, there is degradation when we switched to the MIDI-to-Audio Synthesis systems. So for this Talktron-based system, there is no difference among them that is significantly different, except for these two pairs. I'll just play one sound from one of the systems. So as you may hear, the pitch is reasonably okay, but the quality of the sound is not as good as the copy synthesis case. So no matter which variant of this Talktron we use. There are more results we can compare. For example, how the performance net is quite close to the Talktron in this case, probably because the task is to learn the mapping from well-aligned input to the output. But we should point out that although the subjective evaluation is close for these two types of acoustic models, there is difference in terms of the pitch distortion. So this is quite important for the music application. So if we measure the pitch distortion on a single note, we can notice that the Talktron system much lower than the performance net based models. So that's one strong point about the Talktron models. So that's basically all the results I want to explain here. Quickly wrap up. From this experiment, we notice how TTS methods can be applied to the music audio synthesis. And I think similar to the TTS, one bottleneck of the performance is on the acoustic model. The waveform model can work quite well in the copy synthesis scenario. I think it's somehow better than the physical model because the physical model or the sample-based model can't learn all kinds of effects in the natural sound. For example, the room reverberation. This on the waveform model. Acoustic model, while the Talktron-based system can work reasonably well, but there is still room for improvement, especially to learn alignment for longer sequences, and also for the more difficult scenario where we want to map the simple MIDI into the professional performance. So this will be the future work. And that's the contents of this talk. Thank you for your attention.